In this demonstration, you will see how to compute simulation-based frequency response of a Simulink model. Simulink Control Design provides tools for computing exact linearization of a Simulink model. In certain situations, the exact linearization will produce zero linear model. This can happen when your Simulink model has such nonlinearities as triggered subsystems, like in this case, or pulse width modulation, or state flow diagrams. In those scenarios, you need to compute frequency response of a Simulink model using simulation. You can do that by injecting sine stream or chirp signals into the input of the model, logging the output signal, and computing the FFT. All of this is automated using a GUI in Simulink Control Design or a couple of simple commands. Simulation-based frequency response estimation is also useful for validating the results of exact linearization. So let's look at this specific model. This is a model of nonlinear engine dynamics with an input of a throttle angle and an output engine speed. We specified input and output linearization points accordingly. So let's start by trying to linearize this model using exact linearization. We'll open up Linear Analysis GUI, and in this GUI we'll use model IOs and the initial condition to linearize our model and plot the results in a body plot. When we do that, we get this plot and we get the new variable linsys1. If you look at this variable, we see that the results of exact linearization are 0. So this happens because our model has a triggered subsystem. So to calculate the proper frequency response, we'll use simulation-based frequency response estimation. For that, we'll go into this tab and we'll create an input signal to inject into our Simulink model. We can select a sine stream, fixed sample time sine stream, chirp, or random signal. Let's use a sine stream. We can specify the name, units, radians per second or hertz, and the simulation order. One single simulation for all frequencies or one simulation per one frequency. If you already have a linear model in our workspace, we can initialize frequencies and parameters of our sine stream signal based on that linear system. In this case, linear system is 0, so we are not going to do that. Instead, we'll create the input signal from scratch. We'll specify it as a set of frequency points from 0.1 radians per second to 10 radians per second, and we want to have 30 points spread logarithmically. So let's press OK. We now see those 30 points created here, and to edit the properties of our signal, we can select the frequency of interest and edit the amplitude of the signal, the number of periods that we'll run each frequency for, and when we assume our signal reaches steady state. In this case, we assume it happens after one period. So we press OK. This creates an input signal in sine1, and we'll use this signal with model IOs and the model initial condition to estimate the frequency response of the model and plot the results in the existing body plot. And we'll also look at some diagnostic tool that will help us understand the results. So let's press estimate. This starts the calculations. And now if we go and look at the RPM plot in our Simulink engine model and zoom in here, we will see what is happening. Simulink is running the model with that signal that we just created injected at the input. So we see those different frequencies running through the model. And as the simulation time progresses, we see the higher and higher frequencies being run through the model. Finally, when the calculations are completed, when the simulation is run, Simulink Control Design computes the FFT and plots the results. And we get two plots. The first plot is the body plot that we asked for. So here we see those 30 green points. These are the frequencies that we asked to calculate frequency response at. And in the diagnostic viewer, we see the same body diagram magnitude. And we see filtered steady state time response and FFT of filtered time response. And this is shown for a specific frequency range that we select in the body diagram. So we can select a specific frequency. for example, this point, and see what happens for this point if indeed the steady state time response is at steady state. If not, then maybe we need to specify the number of settling periods, increase that number. And we see the FFT of filter time response, and that lets us see the contribution of this particular frequency and then contributions at some other frequencies. And so typically we want to see those other tail frequencies very small. So this shows us that our frequency response that we just calculated is good. And now we can take this variable that we obtained and copy it into MATLAB workspace. So now if you go into MATLAB, this variable is in MATLAB workspace. And if you look at it, you'll see that's an FRD object, frequency response data, with a vector of frequencies and values. And now we can use that object for further analysis and control design using tools such as LTI Viewer and SISO Design tool. This concludes the demo.